Now, when it comes to studying dynamic response, and in particular dynamic response which may or may not involve oscillations, like ringing like this is ringing, we use a definition which is, has roots in the history of control systems. And so let me show you how that goes. Here, for example, might be some quadratic. Now this, I urge you to remember, this is not a standalone. There might be lots of other terms and in the open loop transfer function or the characteristic equation, and I'm just pulling out one of them out of the open loop transfer function, or the closed loop for that matter. I'm just pulling out one, s squared plus as plus b. I don't even know what that is. You know, if we use the quadratic equation, it might turn out to be two exponentials multiplied together. It might be an exponential times a sine or a cosine. So we don't know without working it out what that will be. But it has become common practice to make an identification between an expression of quadratic behavior like this at the top and a sort of a standard expression. So let's go through this standard expression. We have just by definition, s squared we will write as 2 times zeta, which is a Greek character, times omega n, and that's called the undamped natural frequency of the system, and here's omega n squared. Omega n is obviously the square root of b, as you can see. Omega n must be the square root of b, because these two things have got to be the same. So a must be equal to all this stuff. And so I've already solved for omega n. I can solve for zeta by taking 2 zeta omega n and set it equal to a, and there's the result, that we have the definition of both the undamped natural frequency and the damping coefficient.